Now let's start to think about decision theory in the context of supervised learning in particular. So decision theory for supervised learning. In supervised learning, we've got some data, right? We've got our x's and y's. Each x is typically some vector, for example, and the y's could be like the class or the value in the case of regression. So we've got our data, and then we get to observe, well, we get some new x, and we have to predict the corresponding y for that x until we predict a y hat. So let's think about what this looks like, what decision theory has to say about this. Let's think about two cases. First, let's think about case 1. Let's say we're given a particular x, like I mentioned here. We're always given our data. Let's suppose we're always given our data, and now let's suppose we're given some x and we have to predict a y for that x. And thinking about decision theory, what y should we predict? Well, we should predict a y to minimize our loss. So we predict the y hat to minimize this loss, where y is the true value. But the problem is we can't exactly do this because we don't know what y is. If we knew what y is and we knew what the loss function was, then we could minimize this, but we don't know y. We don't know the true y. So it's a little bit ill-posed. And let's think about another little more general case where we don't know what x we're going to be asked for. We're just given this data, and we have to choose some function f. So f is going to be like our classification function or regression function. It's going to take x's to y's, and we have to choose some f to minimize our loss f of x, but we don't know what x's we're going to be asked for. So again, this is a little bit, what does this really mean? Minimize this, but for what x's? So here we don't know. Here we don't even know what x is, so we don't know what x is going to be or y. Oh, x or y! Exclamation mark. So this is, if this one was ill-posed, this is even more, in some sense, even more ill-posed. But probability will come to the rescue. So what does probability have to say about this? So probability says, well, probability would tell us to think about these as random variables and go for the small, so go for small loss on average. So let's think about putting this in a probabilistic framework. Here everything was deterministic, and now let's keep our data. Let's just keep the data deterministic like that. Let's not make that random for now. But let's suppose that this x and y is random. So x is a random variable, and y is a random variable. X is the thing we're going to have to predict a y for, and y is the true value. And let's suppose, so probability says put a probability distribution on these, and let's suppose these are discrete for now. So let's say these are discrete for now. We can generalize it. We can generalize it later. So P is a PMF. So what does the average mean? Average in probabilistic language, well, that's just the expected value. So let's think about 1 here. Now that we have this little more, a little bit more, maybe more well posed, let's think about if that helps. We're given x, we want to minimize this loss, and we're going to take, so what we're going to minimize now is the expected loss. Our average loss is our expected loss. So what is that? Expected loss of y and y hat. And in the case 1, we're given some little x. So we're fixing some little x, and we have to predict a y hat for that little x. So we're going to predict some y hat. Here we're conditioning on a particular x, so this is the conditional expectation given that x equals little x. And that's why we don't have to make this y hat random. So it's this conditional expectation. And what is this? Well, we just use the definition. So since we have a PMF, we're going to sum over the values. Y is the random thing that's left over here. We're going to sum over the possible values that y could take. And I'll just put this capital script y for all the possible values. And we've got loss of y with y hat times the probability that y equals y given x. Just the conditional probability. That's just the definition of the conditional expectation of this thing. And now we have a well-defined problem. Well, it's a little more well-posed. We might not know what this conditional distribution is, p of y given x, but if we can estimate it, or maybe if we assume a particular p of y given x, then this is at least a well-posed problem. So we can minimize this thing. Now let's think about what this looks like in a particular case. We defined the 0, 1 loss before. That was this thing. It's 0 if we're right and 1 if we're wrong. And let's look at what happens here if we plug in 0, 1 loss. In this case where we know x, what x we're going to be asked. So we've got this thing equals x. I'm just copying this. And now this part, when y is, when y is equal to y hat, then it's 0 and it's 1 otherwise, so it's the sum over y's not equal to y hat of this conditional distribution. And this is 1 minus the probability of that y equals y hat given x, because if we move this part over, then we get the sum over all the y's, and that's equal to 1, because this is a conditional probability mass function. So that's nice, and so that's a nice little expression for this conditional expected loss, which is the thing that we are wanting to minimize. Thinking from a decision theoretic sort of perspective. And so let's try to minimize this. What happens if we try to minimize this? Let's say that we want to predict the y hat, which is the minimizer, the argmin over all y's of this conditional expectation. The loss given x equals x. And this is the same as, so if we're minimizing this negative thing, that's the same as maximizing. That's the arg max over y's of this, of the probability of y given x. And this has a very natural interpretation. Thinking about, we're trying to classify So think about what we're doing here. We're given some x, and we want to choose a y that is a good class for that x. So the most natural thing to do, in some sense, is to choose the y which is the most probable y for that x. That's exactly what the 0-1 loss, what minimizing the 0-1 loss tells us to do. So we're going to choose the y hat to minimize, choose our y hat, our prediction, to maximize the probability, this conditional probability. It's most likely, so it's like the most likely class. That's what this is. And this is for classification. So the key quantity here, let me just point out, this conditional distribution P of y given x is the key quantity that we needed to solve this problem. So this is the important piece.